Another test for convergence and divergence on a series is the alternating series test. And just as its name implies, the test deals with series that contain both positive and negative terms. And the simplest such series is an alternating series whose terms alternate in signs. It can either start negative and then turn positive, negative, positive, meaning the odd terms are negative, the even terms are positive, or it could be the other way around. You could also have series that might have two positive terms and then two negative terms and then two positive terms and alternate that way. But we're just going to restrict our view to looking at the alternating series. A little bit of background in a theorem about the alternating series test. Okay, it says let a sub n be greater than 0. The alternating series can either be given by this expression or this expression right here. Okay, and the only difference between the two is what term begins the series. Is it positive or is it negative? And if we look at both of these series right here, if n is 1 here, then the first term and all odd terms are going to be negative. If we start with n equals 1 here and the exponent is n plus 1, then the first term and all the odd terms are going to be the positive terms. So just the two different ways that you can write, or two ways that you can write an alternating series. Okay, this is a test for convergence. So the series, an alternating series will converge if the following two conditions are met. Okay, ignoring the alternative, the negative sign here, just looking at the a sub n term. Okay, an alternating series will converge if two conditions are met. The first one has to be that the limit as n approaches infinity of the nth term does go to 0. And the second condition is that the term that follows a preceding term, the term that comes after the preceding term, has to be smaller than the one that comes before it. And I think that makes sense, that if we want our series to converge, that later term should be smaller than the previous one to it. And the notation that supports that is this. Maybe. There we go. Okay, let's look at some examples of some alternating series here. Okay, it's very clear this is an alternating series just because that identifies it as such. Let's consider a sub n being 1 over n. Okay, now you might remember that 1 over n is the p series that diverges. Well, this isn't a p series because we have an alternating situation here. And it probably wouldn't hurt to kind of generate a few terms with this, just to get an idea of what you think this series might do, converge or diverge. Okay. All right, anyway, the first thing that identifies this as an alternating series is this right here. So we're going to go with the two conditions. Let's see. Is it true that the limit of the nth term as n goes to infinity is equal to 0? It certainly is. So condition 1 is met. Check. Okay, and then for condition 2, we have to just generate a few terms here to compare them. And kind of like the DCT, the direct comparison test, I'm going to generate the a sub n plus 1 term. And all that means is look back here at 1 over n. Everywhere you see n, replace it with n plus 1. Because that's the term that follows 1 over n. Okay. I'm going to put a question mark up here. Is this term less than or equal to 1 over n, which is the a sub n term? Yep, because no matter what n is, this denominator will be larger than this denominator, and this larger denominator creates a smaller value in the fraction. So the question mark is no longer needed. I know that's a true statement. Okay. Oh my goodness. Both conditions are met by the AST. So therefore, by AST, this series converges. It's kind of interesting because just the harmonic series 1 over n diverges. Okay, let's look at another example. We have to test to see if this series is convergent. Okay, now this is a test again. AST is only for convergence. All right, number 1. All right, let's look at just this part of the series right here, and let's find the limit of that nth term. Okay, well, think rational functions, think end behavior, think comparing your exponents like we've done before, and we can certainly do that. The exponents are the same. Okay, so the value of this limit is going to be 1, which does not equal 0. So the alternating series test does not apply. But what's revealing here is this, that because of condition 1 and condition 1 failing, okay, because 1 fails, condition 1 fails, we know that this is the nth term test for divergence. So I'm going to say, okay, well, I'm done with the AST. It's not going to, prove that something converges. So therefore, by the nth term test for divergence, this series diverges. And I'm not going to write that down twice. I'm just going to say by the nth term test, the series diverges. I'll just put diverges right here. Okay, we identify this as an alternating series. Okay, so just kind of recapping, this is definitely not geometric. The nth term test might apply, even though it's alternating, that's fine. But what I want to make sure you remember is that for the integral test and for the DCT, the direct comparison test, those tests are only to be used on positive terms, and obviously this is not. Okay, all right, so condition 1. Ignoring the -1 to the n, just looking at the nth term, irregardless of the sign. Okay, we see that that goes to 0. So we're well on our way here. So condition 1 is met for AST. Let's look at condition 2. The term that follows this term is going to be 4 over 3 times n plus 1 plus another 1. So what you do is you just replace the n with n plus 1. Okay, and is that less than? Is it less than or equal? Yes, less than or equal to 4 over 3n plus 1, which is the nth term. Okay, I guess we can kind of reason through this, or like we did for the DCT, you could actually plug in a few values for n and see what happens term by term. But I think we're going to see that this denominator right here is going to be larger than this denominator for any n value 1 or higher. So if this denominator is larger, the value of this fraction is smaller. So we're going to say that this series up here converges because both conditions are met. So the AST is a test for convergence. Okay, so let's see, therefore, by AST, etc. Okay, we see this as an alternating series. I'm going to try the first condition, the limit of the nth term. I just imagine this being a rational function where the highest exponent is 1. This exponent in here, the highest one is 2. So it's an end behavior kind of situation, and yes, this limit does go to 0. So condition 1 is met. Let's look at condition 2. Everywhere you see n, replace it with n plus 1. just a representation of the n plus 1 term. Okay, are all those terms going to be less than or equal to the original term or the nth term? Okay, this one's just a little bit more involved because look at the numerator here. The numerator n plus 1 changed. So my numerator is getting bigger here. My denominator is getting bigger here. I'm not quite sure if all these terms are going to be smaller than these terms right here. Again, if you're not sure, go ahead and produce a few of the terms. So if n is 1 here, I'm going to get 2 over, if n is 1, that's 2 squared, 4 times 2, 8, 9, 2 ninths. Okay, then over here, if n is 1, I'm going to have 1 over 3. And 2 ninths is definitely smaller than 1/3. Okay, you could do a couple of terms comparing them this way. If n is 2, then I'm going to have 3 over, maybe 3 squared or 9, 18, 19. Okay, if n is 2 here, I'm going to have 2 over 9. And 2 ninths is definitely larger than 3 19ths. And so I think this pattern is going to continue. So I'm going to say, you know what, condition 2 is also met. Okay. So the whole therefore. Converges. Okay, let's look at this example down here that has terms already generated for us. It's not written in the concise notation, the sigma notation. Okay, so you know, usually you're given the concise notation, but what happens if you are presented with this type of series here? We can definitely see it's a series. We're adding some terms, and they're alternating in sign. We have positive, negative, etc. So it's an AST. It's an alternating series. It's an AS. It's an alternating series. So let's see if this this series converges by the AST. So condition 1. Limit as n approaches infinity. And we don't have an expression for the nth term here. So we don't have a specific, you know, nth term. So I'm just going to put a sub n to represent that term out here. So it appears to me this is 2, this is 1, this is 1, this is a half. Ooh, that's 2/3. That's an interesting one. This is a third, a half, and a fourth. I do feel like the terms are going to 0. So I'm going to say that the limit of the nth term is 0. And examining this series in a little more detail, we can see what's happening here. Both of these terms are over 1, with 2 in the numerator of the first one and 1 in the numerator of the second one. Both of these terms are fractions with 2 in the denominator, then 3 in the denominator, then 4 in the denominator. So they're like pairs, you know. So here would be 5, 5 with a 2 on top and a 1 on top on this one. So I'm going to assume that the limit of the nth term does go to 0. All right. So now the next thing to check is, are the terms getting smaller? Is it true that a sub n plus 1 is always less than or equal to a sub n? Well, no, we can find, you know, an example, a counterexample. So 2/3. And remember, we're looking at the absolute value of the term. So 2/3 is not less than equal. That's a not less than or equal to the 1/2. So we were looking at the comparison here. All right, so this test is going to fail. We say that the AST test fails because of condition 2. Does that tell us whether or not the series converges or diverges? No, it only tells us that we can't use the AST test, or the AST. That's all it tells us. So we would have to provide another test or do something else to determine if this series converges or diverges. But at this point, we were just using this example to see when the AST test would fail, and it is in this one right here. We're not going to do any further study with this series, however. Okay, so one more video to look at the alternating series remainder.